Right, so morning everyone. Nice to see quite a few of you still getting up at 9 o'clock in the morning to listen to me. It's very encouraging in some ways. So again, I'm assuming everyone can hear me. If you can't, just say so. But I'll just carry on because I'm quite confident now that you can hear me. Yes, great. Thanks, Don. Good. Right, so we have finished, you'll be pleased to know, the circuit analysis part of the course. So there's sort of what I'll call the boring bit. Excuse me, a bit of a cough this morning. And so now we move on to something that's a little bit more interesting, I think, anyway, a bit more abstract, maybe you have to think about it a bit more, to transistors. And transistors are obviously a fundamental part of electronics, and we need to have an understanding, at least at a behavioral level, of how they work and what's going on. Hopefully you've got a good idea from the semiconductor course of how they work at a sort of a low level, and then we can understand how to build circuits from them, where the limits lie, and how that leads on to other circuits as well. So this part of the course then, which is from now until the end of the semester, as far as I'm concerned anyway, is we're going to look at transistors. There's two types of transistors. There are bipolar transistors, so we'll spend some time looking at those and how we can model them and convert them into a form that we can put into circuits to analyze using the linear theory that we've learnt over the last few weeks and hopefully last semester as well. And then we'll start looking at, and once we're happy with that, we can start looking at how to actually use them as amplifiers and do something useful with them and understand their limitations. We'll then look at another type of transistor, which is called a field effect transistor. We do them after bipolar transistors. In fact, they are invented before bipolar transistors, and we'll look at those. We'll understand roughly how they work then, because they're still transistors, so we'll have done it all from up here. We'll look at some models as well, and then we'll look at their uses as amplifiers and some things that they can do that bipolars can't do, which is analog switches is one example of that. And then, having understood the limitations of what's going on in here and how amazing these transistors are, but actually how rubbish they are as well, we put a few of them together to make this thing called an op-amp, or operational amplifier. And this allows us to make something that's close to a perfect amplifier, and we'll have defined what a perfect amplifier is by then. And once we've got that, we then really bizarrely don't really care about what's in the amplifier. We can start to use it to define more interesting functions, such as adders, precision diodes, and frequency dependent circuits, which you might have heard of as filters. So that's what it's all leading to. We learn about the transistors, and then we learn their limitations, and then we go forward with that. Do we do MOSFETs? Yes, we do. They're part of FETs. They're just a subdivision of field effect transistors. So we do MOSFETs. Not in a great deal of detail, but enough to know how they work anyway. Okay, so transistors, basic types and how they work. So the invention of the transistor, this is a page from the original patent, 1951. Some people will tell you so it was filed in 1948, but it was granted in 1951. Patents take a long time to get granted. And these are some diagrams of what a transistor looks like, and they're probably meaningless, but you'll notice as we go through that some of these diagrams that appeared in the original patent, this kind of one for example, are still used today to describe exactly how transistors work. So Mr. Shockley hit it right on the head with these diagrams here. And as I said briefly, two types of transistor we're going to consider. There are bipolar, which is bipolar means basically two directional, and these are in two flavors, what's known as an NPN, and we'll look into why they're called NPNs in a minute, and PNP, which is just a reversal of this. And then we look at the field effect transistor, which is abbreviated to FET, which tends to be unipolar. They're only sort of one directional things. And there are two types of those. We have a junction field effect transistor, which is the simple and early device, not used that much now, but useful to understand. And then we look at this thing called a MOSFET that Mr. Samuel Stevens has mentioned, which is a metal oxide silicon field effect transistor. So you can see the abbreviations get longer and longer as we go further and further forward in time. Okay. So bipolar transistors, two flavors, NPN and PNP. So these are diagrams similar to that were in the patent, and they're made of two different types of silicon. So we have something called an N-type silicon, a P-type silicon, and another piece of N-type silicon. And the difference between N and P-type silicon we'll come across in a minute. You should have understood that maybe from Fred and his course on Garan on semiconductors. But in case you're not, we'll just briefly go over it so you can see it in context here. There are three terminal devices. This is sort of how they're made in a schematic form. This is what we would draw them like on a schematic diagram. So this is the symbol, if you like, for a transistor. And there are three terminals involved. There's a C, a B, and an E. And these are abbreviations for collector, base, and emitter. And these names go back to the times of valves, which were the precursor to transistors, when these names actually had a bit more sense. You know, it will collect electrons, this would emit electrons, and the base would, or the gate would control it. So again, it's looking a bit like a node, so we'll have some definitions, and we know all the define currents going into these nodes. So we've got collector current, base current, and emitter current, and they're defined as going in. Obviously, they can't all be physically going in, so at least one of these is going to be defined, is going to be a negative current. And then the PNP is just made slightly differently with different materials, okay, and we end up with a symbol that's slightly different. So on the NPN, the only difference is an arrow coming out in the emitter, and on the PNP, we've got an arrow going in on the emitter. And I've labelled a couple of other voltages on here as well. These are quite important voltages when it comes to analysing these volts, so we need to have an idea of where they actually are. This one, VBE, which is the voltage of the base with respect to the emitter. So what voltage we've got here, measured with respect to here, is an important, probably the most important driving voltage in a transistor. VBC is the base collector voltage, not so important, but we still need to understand a bit. And there's one that's not drawn here, which is VCE, the voltage of the collector with respect to the emitter. And these are the definitions that we're going to be interested in going forward. So how do these things work? Current flows through these things, physical current flows through these things in this type of direction. So what ends up with is you end up with a big current, or largish current, flowing from the collector to the emitter in an NPN transistor. So it's just flowing straight through here and out. And in addition, we have a smaller current coming into the base, which joins up with this current and also flows to the emitter. So it's all being emitted from the emitter. It just joins up. And the way the transistor works, in principle, is that a small current going in here can control a much bigger current coming through here. So it's like, you know, this current here controls the tap. If you think of it as a water tap, you turn the tap on, you get a big flow of water. So the base current is the sort of control of the tap in that respect. In the PNP, it's the other way around. Physical current flows into the emitter, out of the collector, and a small amount of it then flows into the base. So again, if you can control the value of this current here, you can control the value of this current going forward. So get that into your minds. What we've got here is something that just controls a small current here, controls a big flow of current here. But remember, it's current. Current is the fundamental thing here. Think of it as a current controlled valve. For the PNP, why is there a current IB colliding? Let's have a look. There's not colliding. This is just a definition. We're defining IB as being positive. So in this case, because the current comes out, it would end up being, in any calculations, it will come out as negative. That's it. It's just definitions. This is the real direction of the current, the red arrows. The black arrows are just the definitions of the positive direction. Okay? Right, so notation. We have to have some notation. It gets a bit tricky with transistors, so we have to be aware. And I'm noted for making a few mistakes in this sometimes because of self-capitalization in Microsoft's products. So we split transistor circuits into what's called a large signal and a small signal, and we will define those going forward. But basically a large signal is the DC conditions. So these are currents that flow continuously and don't change once you've turned the circuit on. and we define these as being capital letters. So this is a capital I and this is a capital C, sometimes difficult to tell, and this means that we're talking about the DC collector current. Okay, so this is not changing, this is fixed. Capital I, capital C. I is current, C means collector. So the opposite of that is something called a small signal, which is where the signals are, so the AC, so we've separated DC and AC. Again, don't worry too much about that at the moment. And we define those as lowercase letters. So this is a small I and this is a small c. And you can see that difficult to tell the difference between the C's. But anything in small letters means that it's a changing current, and this will be the AC collector current because it's changing. So we define it with small letters. And so the combination in the circuit, so it's a form of superposition, is the combination of what the DC system is providing and what the AC system is providing, and we add those together. And so if we look at the instantaneous total signal in any of these circuits, we can say that it's a combination of the DC and the AC. So we have a capital I from this bit and we have a small c from this bit. So there's some logic to it. So we just have to be aware that the capitalization of voltages and currents in these types of circuits is important. This is useful because we extend the idea of superposition and we analyze transistor circuits in two chunks, a DC chunk and an AC chunk, and the reason for that becomes apparent as we go forward as well. So it's unfortunate we have to hold a lot of these ideas in our minds before we can actually get on to actually looking at how these transistors work. So the basis of transistor action in some more detail. So if we thought about the structure of our PNP and our NPN with our N-types and our P-types going forward, you could visualize the transistor as being two diodes back to back, diode being a PN junction. Okay, so we've got a junction between a piece of P and a piece of N. So we could draw it in this kind of form, two diodes back to back with the connections like this. But that would be intuitively a bit of a strange way of looking at it, because with two diodes back to back, at least one of these diodes is going to be reverse biased, which means it's going to block current, if you think back to the semiconductor course. So on the face of it, there's no real way that current can flow in this direction and come out, or indeed in the other direction and flow out, because this diode may well be forward biased, but this one would be reverse biased, so the current wouldn't be able to get through. Possibly it might come out the base, but it can't get through. But I've just said in the previous slide that it can get through, and actually it's quite a big current, and the big current flowing through here is controlled by a small current going into the base. So we have to sort of think about this in a little bit more detail, and this is effectively the magic of the transistor, is how something that's actually made up of two diodes back to back can produce or allow a significant current to flow through it, because one of these things is the wrong way around. Okay, so in formal terms then, when the base collector junction BC is reverse biased, so it's a negative voltage on it, excuse me, and the emitter base is forward biased, most emitter current flows in the collector. So any current coming into here does actually flow out of the collector through this reverse biased diode. So we've got to look at this in a bit more detail to figure out what's going on here. And the base current is small as well. Now, there's a little note at the bottom here. We are considering conventional current, and in brackets holes. And so we have to think about what is a current. And normally a positive current implies the electrons are flowing the opposite direction, if you remember back to your physics. Gets a bit confusing for a little bit, but after that it's all fine and we can forget all about it. So just bear that in mind at the moment. So let's look at semiconductors in a bit more detail. So this is a piece of silicon, pure silicon, nothing else in it. It's a crystalline structure, so these are silicon atoms and they're regularly arranged in a crystal format, and the electrons are tightly bound in this type of configuration. So silicon in its pure form, so these little bows, if you like, or brackets, they're electron bonds, and they're showing how the electrons effectively are shared between the silicon atoms and are pulled together. So think back to your chemistry. Otherwise, if you're not familiar with chemistry so much, these are silicon atoms and these are the electron bonds, and there's always four, and when it's in, there are four or 8 of them in the outer shell, when that is the case, everything is very stable and doesn't want to change. so it's very difficult to actually make this conduct really well. So as it says, electrons are tightly bound, poor conduction. It's all very stable, and there's no electrons free to move, so things are not going to conduct very much. Okay. So this is when it starts to get a bit clever. So there are thermal, agitation and quantum effects. Okay, but basically there's some energy involved in here because it's at a certain temperature that's above zero. So these atoms, or these electrons, are bouncing around in their bonds. They're jumping about all over the place, but they're being held close. They're not allowed to escape. But occasionally, because of probability and quantum effects or whatever, these electrons could just randomly get enough energy to escape their bond. So this red dot could be an electron. Here it is. It's bouncing around, trapped in its cavity. Suddenly, because of quantum effects, which is a great get out, it escapes from the bond and is now bouncing around over here, and it's not trapped by the atom, so it's free effectively to move about. And if an electron can move about, a moving electron is a current, so we can have a current flowing because this electron has escaped. Right. It will leave behind a hole, because if the electron here has escaped from this bond here, that bond is now broken, so that it could in principle receive the electron back in again. So if this loses energy, it could fall back into that and make it stable again. But if it doesn't, if it's out here and then for some reason moves away, what we've left is an uncovered positive charge in this atom, and it's a bit unhappy about that, and so it's trying to attract an electron to fill the gap. And this uncovered positive charge is called a hole, because it's a hole that an electron could fit into. So very imaginative, these physicists, when it comes to naming these things. So what we've got now is an electron-hole pair created by thermal effects, because the electron has vibrated itself out of the bond, left behind a hole, and we've got a free electron. Note the total charge balance across this piece of silicon hasn't changed at all. There's still the same number of positive and negative charges. It's just they've been slightly separated, and it's the separation of charge that leads to all kinds of interesting effects in the silicon. Right. So this electron is now relatively free to move through the lattice, or the structure of the crystal, and that's called an electron current because it's electrons that are moving. Okay. The hole, which has been left behind, can't move. Or can it? Well, because I've asked that, the answer is obviously yes, because we talk about hole currents anyway. So it's relatively easy for a neighbouring electron to jump bonds. So he escapes from his own bond and then falls immediately into the hole of the bond next to it. So the hole has moved, say, from left to right, but the electron has moved from right to left. Okay, so that's saying the same thing. And that is still a moving charge, because it's a positive charge or gap that's moving, and so we can still think of that as holes. We can think of those holes flowing, but the reality is it's still electrons flowing, because it's the electron that's making the hole. It's just filling the hole next to it. And normally when I give this lecture, I then say, well, the best way, particularly for majority of students anyway, to get a visual effect on this is to go down the pub, but we obviously can't do that at the moment. But I can explain what happens when you go down the pub and you order a pint of Guinness, and if you get a good one, you'll look at it and you will see bubbles going downwards in the Guinness. And this is a very strange effect to look at, but if you look very carefully, you'll find that it's not bubbles going downwards. The bubbles are still going upwards. It's the gaps between the bubbles that are going downwards, and this is the equivalent of a hole current. The bubbles, being the electrons, are still moving up, but it looks like the bubbles are actually moving downwards, because it's the gaps between bubbles which is going downwards, because they're in the majority. Usually takes a few pints to get a handle on this, but it's worth it. So at the great end of this great pandemic, when you can all go down the pub, or if you want to go down the pub, or just get someone to buy a pound of Guinness and have a look at it. Don't have to drink it if you don't want to. Just look at it, because it's very educational to show the nature of hole currents. Right, but I've just said that silicon's a bit rubbish at conducting electricity, which sort of flies in the face of all the evidence, really. But that's because it's intrinsic, or it's pure. Does it have to be Guinness? Sadly, it does. Or something that's really, really frothy. Usually something that's been gassed up with nitrogen rather than carbon dioxide, for rules best known to itself. But feel free. You might actually, that's an interesting one. You might try it with Coca-Cola and add some sugar. It gets a bit violent, but if you do some controlled experiments, you might be able to get into a case where you can see what's going on. There you are. That's the sign of misspent youth. So, if we add dopant atoms, we can change the number of holes for electron. So here's our crystal structure of silicon, and we've replaced one of the silicon atoms with, in this case, a phosphorus atom. And phosphorus, the difference between it and silicon is it's got an extra electron. So it's got an electron that's loosely bound to it in the normal conditions, but it's easy for us to kick this little black electron out into a higher orbit and get it to conduct. So this allows us a sort of a surfeit or an excess of electrons that are relatively free to make move. And in this case, electrons are the majority carriers because we haven't really left any holes behind. The other thing we can do is we can replace a silicon with something else, in this case an aluminium, and that's got an incomplete outer shell, so there's a gap already there, so we've already got a hole. And this gives us a surfeit of holes, if you like, in the material, so we can have hole currents. So remember, it's still electrons moving, but electrons moving from here to fill the hole, and then from here to here to fill the hole. And holes become the majority carriers. So that's the difference between N-type and P-type. It's what you've put in to dope it to increase the number of relatively free electrons or holes. So quick reminder of the periodic table. Silicon's over here, and you can see that phosphorus is 1 to the right, which gives us the extra electron, and aluminium is 1 to the left, which gives us the hole. Now, aluminium is not normally used for various reasons, one of which is the aluminium atom itself is actually very mobile through the silicon and can move. It's not locked into the crystal lattice particularly well, which is not good for a long life of transistors. So you'd normally go for somewhere else in this group, and boron is the sort of weapon of choice in that particular case. So boron and phosphorus would be probably good choices for doping. Anyway, we're not that interested in that, but that's just to give you what's going on. So if we then join two bits of silicon together, a p-type and an n-type, so one's got a surfeit of basically free electrons and one's got a surfeit of holes that would like to receive the electrons, something very interesting happens at the junction between the two. The majority carriers diffuse across the boundary. It's all driven by probability and Brownian motion, that kind of thing. So a bunch of free electrons here, there's going to be a gradient, and they're going to want to fall over the boundary. And likewise, the holes will sort of diffuse the other way. And eventually, it will leave a charge behind which will try and pull them back. So you end up with this sort of balancing effect. But what's happening at the boundary is the interesting thing. So, for example, holes will move from left to right, leaving uncovered negative ions in the crystal. And similarly, electrons move from right to left, leaving uncovered positive holes in the crystal. So we end up with this sort of strange area. It's very, very thin. The overall charge is still 0 because we haven't lost or gained any charge. We've just redistributed the charge under sort of diffusion effects. I'm not going to answer about how we get neutral. We don't get it. There is an area where it is completely neutral, which you can see, but it's due to because it's just Brownian motion. If you think back to your experiments on Brownian motion, that's probably the easiest way of thinking of what's going on. I'm assuming you did Brownian motion at school. Can't see why not. So this leads us to, so if we accept this is going on, we've got this sort of area of diffused charge going on. The charge density, so how much negative and positive you've got going on, looks like that. And if you average all these, they average out. If you integrate this, if you integrate charge density, you end up with electric field. So you end up with an electric field distribution across this diffusion zone, and if we integrate that electric field potential, we end up with potential for doing work. So one way of thinking of this is the potential is the work done by a hole in trying to cross the junction from left to right. So we've got a hole over here and it wants to get over here for some reason, best known to itself, Diffusion is driving it a little bit, so it's got a little bit of bias going this way. If you give it enough energy to give it this amount of potential, it can cross the junction completely, and then once it's over here to this point here, there's no more electric field driving it, so it's free to just sort of mill about once it's got over here. If you don't give it enough energy and it moves this way, it comes to do some potential, does some work to try and get up this potential, but hasn't got enough, and then it will be driven back by the electric field. So if it's got enough energy, it'll escape into here. If it hasn't got enough energy, it will get bounced back again, and you've got millions of these things bouncing up and down up this hill, and this is called a potential hill. So if it's got enough momentum in terms of energy to get up this potential hill, then it can get from the P-type into the N-type, but there's this sort of barrier of electric field that's stopping it and repelling it back again, and they're all trying to do this. So if you give them enough energy, they will get up the hill. Okay, and one way of giving them some energy is to apply an external voltage. So if we put a potential across this thing now, a forward bias acts to reduce the potential hill, or if you think of it the other way, it gives the holes and the electrons more energy to get up over the hill. Thus it's easier for them to cross. So if the forward voltage exceeds the junction voltage, then the limit to current flow is just the resistance of the semiconductor material. If we give this enough voltage, we will force current through here, get up that hill, and it's no problem, and it just flows straight through the material. Okay, so there's a little animation there, you might not have seen it, but the red bits have now turned into black bits, and there's very little gap for them to cross. So if you reverse bias it, so here's a little red area here, standard diffusion zone. If we make this voltage bigger in the wrong direction, if you like, reverse bias it, we make this diffusion zone bigger, and therefore things have to have more energy to get up the hill to escape through here, and the depletion region gets bigger. Okay. Now, remember, we said that quantum effects can allow these whole electron-hole pairs to just form spontaneously, randomly, because of quantum effects. So they're forming all over the place, randomly, depending on the temperature. And if you get one in this forming in this depletion zone, which can happen, then quite often, what would normally happen is when they're in this region, you form the pair, one escapes, and it just drops back into its hole again, and everything's happy with the world. If it happens in this area where there's electric fields in place, the electron and it breaks its bond and goes into a high region, and suddenly is under the influence of an electric field and is whizzed away. And that means it can't then fall back into the hole that it originally made, and so the hole then goes the other way. So this is an electron hole current, and this is what's called the reverse saturation current. And it's basically sort of how solar cells work. So if you imagine that the solar cell is effectively a big p-n junction, when light falls on the junction, it gives it a bit more energy, and this causes more of these electron hole combinations to occur. So an electron gets kicked into a high orbit and then gets whizzed away by the potential. And so as things get hotter, you'll find this reverse saturation current, this leakage current if you like, gets bigger. So that's the nature of reverse currents in these devices as well. There you can see well, there was one formed there. There it goes. See, they get formed and then they get pulled apart by the electric field. Now, so that's all fine. The clever bit is when you add a second junction. So the person who did this was a genius, Mr. Shockley, because you end up then with two diodes, and this is where the two diodes back to back starts to appear. So now we've got a potential hill on this side, as you know, shouldn't be a surprise to us from seen from the previous slides, and then obviously we've got another potential hill going back down again. So in actual fact there's just this sort of little barrier going on here. That's the only thing that's stopping the current flow, and we know that if we just give it a bit of enough energy, we can get the current to flow into that area. And then what actually happens is anything in this area, if it then drifts across here and gets into this area, it's actually accelerated into the p-type. It's saying you shouldn't be here, I'm going to send you that way. Remember, it would have gone that way, but it had enough energy to get over the gap, and this one is just sort of rebalancing it and saying, right, you out. And so once it's in this area, once you've managed to get your electrons or your holes or whatever into this base area, the ones following it sort of push these along, and then when they get to here they just roll down the hill and out the other side. So that's the current flowing. And that is the genius of the transistor. Why, you say? Doesn't sound very exciting to me. Well, let's just look into it. So in a bit more detail then. So if we forward bias this, a hole is pushed across the junction. This is emitted into the base because we pushed it up the hill with this energy from this thing here. It's pushed it into here. It's now in this area. It's free to drift across this area. It's unlikely to hit any of these atoms because they're quite widely spaced. And the ones following it are going to cause a gradient as well, so they're going to be pushed along. And then when it gets to this area, it gets accelerated down the hill and gets pushed out of here. And the ones following go through. So we end up with the current flowing through this thing. And the secret is to make this bit really, really thin. Because then there's lost chance of these excess holes or electrons finding their opposite in the structure and recombining. So we want this to be as thin as possible, and then once we've got them in here, they'll find their own way out from this end. So why is this important? So what this is saying is the collector current, so let's just go back, collector current is independent of the collector base voltage. It's an ideal current source. Because the current coming out of here has to be, if we ignore this one, the current that's coming in here. And the current coming into here, this part of the circuit, is defined by this voltage here. Make this voltage big, we get a big current going in here. Make this voltage smaller, we get a smaller current going in here. But if we ignore the current in the base because it's very small, then everything that comes in here has to come out of here, irrespective almost of what this voltage is. We could make this reverse voltage big or small, doesn't really matter. The only current that can actually flow is what's coming in over here. So what comes in over here comes out of here. This helps it, but is not controlling it. This is the thing that's controlling it. So if we can control this voltage here, we control effectively the current in this loop of the circuit. Okay, so it's a current source because the current here is constant irrespective of what we do to this voltage here within reason. Okay, so adjust this voltage, adjust this current, fixes this current. This voltage doesn't really come into it. So we've made a current source. That's the important thing. We've made an ideal current source. And the emitter current, the current coming out of it, is controlled by the base emitter voltage. Okay, so the other end of voltage. Nearly all of the emitter current reaches the collector. Therefore, the collector current is controlled by the base emitter voltage. So let's just re-emphasize that. The collector current, the current coming out of here, is controlled by this voltage here. Yeah, and that's the key to it. We've made a current source that we can control by a variable. This isn't, so we can go back to our independent sources, and that's what we've made. We've made a dependent source. Okay, so what? So here's our transistor. Here's our controlling voltage. Here's some just encouraging reverse bias voltage, just to make sure that current does actually come out. And we had a load resistor. So remember that a resistor is fundamentally a device that converts a current into a voltage, or it doesn't convert a current into voltage, but it gives us a voltage proportional to current. So a thought experiment. A small voltage change, delta V, between the emitter and the base, so between here and here, so a small change in this voltage here, causes a current change in the emitter in here. So if we change this voltage here, we would expect this current to change because we've given them a bit more energy and they can get up this hill or not. Okay, so we've got delta V giving us a change in current of delta E, delta IE. If all this current passes to the collector, so any current here ends up over here, then the output voltage changes by delta IE because we've changed the current by delta IE from over here. That flows through this resistor, and that will manifest itself as a voltage change across here, which is going to be delta IE times R. And R is something that we have control over. So this output voltage, it now becomes dependent effectively on the value of R. Okay. So specifically A, the gain of this circuit, if you like, or the relationship between the input and the output, which we define as the change in the output voltage for a change in the input voltage. So if we change this input voltage how much of a change in the output voltage do we get over here, is equal to R times delta IE, which is just Ohm's law applied to this, divided by the equivalent on the input side, which is a little r, delta IE, where R is actually effectively the resistance of this term here. So it's a relationship between this voltage and the change in the current over here. So I haven't really introduced that, but R is the dynamic resistance of the base emitter junction, so it's the equivalent resistance between here, and it's usually low, in about thousands of ohms, and that's what we term low in this case, because it looks a bit like a diode, and we know that diodes actually are quite happy to allow current to flow through them. So the relationship becomes, the gain of this circuit becomes R, which is the value of this resistor here, divided by R, which is a little bit uncertain, but it's basically the value of the resistance between these 2 points here, or the equivalent resistance. And as long as R is big compared with small r, then we get a bigger output voltage for a small input voltage, and that's the nature of gain. So that's a very quick introduction to the fundamental idea of gain in the transistor, and it's to do with current gain. So this is the basis of transistor action. Power gain has been achieved as the voltage is increased, although the current hasn't changed much. So power is, remember, is voltage times current. So the current hasn't changed much because all the current just went through the thing, but we've got control over the output voltage gain, so VI can become bigger. And current in the low resistance input circuit has been transferred to the high resistance, or potentially high resistance output circuit. Well, it is high resistance because it's a current source, and the output impedance of a current source is very, very high. And that leads us to this name transistor, which comes from transfer resistor. So I said we'd be picking the pace up a bit now, because all of a sudden in this device we've applied all kinds of concepts that we learnt in the first couple of weeks of what's the nature of a current source, a little bit of mesh, a little bit of nodal stuff, to understand how this transistor works, and it's leapt up a whole level, I would suggest. So you probably want to just reflect upon this and understand where it's come from going forward. So that's the basis of our transistor. We can see that it's got an idea that it can amplify. Even though it's a current source, we can get a bigger voltage out of it by adding a component to the outside, in this case a resistor. And so we would like to come up with some kind of model so that we can include this into our circuits more formally, and then analyze the circuits using the linear theory, hopefully, that we learned a bit earlier. So the physical construction of a diode of a transistor is two diodes back to back, which we said was a bit counterintuitive, but maybe we've got an idea now of the fundamentals of why this becomes a bit useful. It led us to this sort of analysis with our two diffusion zones, and an understanding of current comes in, eventually gets expelled over here somewhere. And so if we think about this, we can apply some logic to this and say, well, actually what we've really got is a diode, which is just this one here. That's that sort of bit of the circuit, which is just this PN diode here. And there's something funny going on with this reverse junction diode, but actually it looks to us like a current source, because it's a constant current source, because doesn't matter what voltage we apply across here, it doesn't really affect the amount of current coming out of here, because it's the current that goes in must come out. So we've made this current source. So the first model of our transistor could be a diode driving a current source of some description, and we just put the wires on accordingly. So that's starting to look a little bit like something that we might be able to analyze, or at least understand in the circuit diagram. So how accurate is this? Is this a good way of approaching it? We just need to have a little bit of a look inside the transistor again and define some other variables. And there's one called alpha. So physicists are nothing if not imaginative when they come to name these things, because there's one other parameter we're interested in, and that's called beta. So we have two parameters in a transistor that we're interested in, alpha and beta. Okay, so that's relatively straightforward if you get that in your mind. So up until now we've always said that let's assume all the current goes through the device. This is obviously plainly not true. Not all of the current gets from the emitter to the collector, and some is lost in the base, this area here, due to recombination of, they just stumble across spare holes or electrons and recombine. And alpha is the fraction of the emitter current reaching the collector. Usually quite close to 1. In an ideal transistor would be 1. All of the current gets through to the collector. So that will be a ratio, or a factor of 1. A little bit of it escapes. So this alpha is a measure of effectively how good your transistor is at letting everything through. So if you just draw it like this, so this arrow here is defining what the current looks like, or the size of the current. So you've got all the current coming in, alpha of it is coming out of here, and a little bit is coming out of this one. And that's relatively straightforward. And if we look at the definitions, we can say that IC is minor alpha IE. So and it says the arrows here show intuitive direction, not the definitive direction. Remember, for definition purposes, all currents are defined as going into the device, which is why there's a negative sign here. Okay, so collector current is equal to alpha times the emitter current. So that's all that's saying. And because of the definitions, there's a minus sign, because everything is defined as going in officially. And therefore IE is equal to minus IC over alpha, if we just rearrange that. So beta relates to the fraction of the current that doesn't make it across the device. Beta can be a large number and is very useful. And we actually introduced ourselves to beta last week without anyone telling us about it in our dependent source example. And actually I need to so the dependent source example that we looked at last week, someone sent me a message saying he didn't quite understand how it worked. The analysis I did with superposition for it. So I've looked at that, and there was a few probably non-obvious steps that I missed out in there. So what I've done is I've re-recorded that example and redone it again with another example to make it clearer. So I'll put a little sub video up onto the Blackboard site probably later today if I get time, that just adds a little bit more detail to the superposition of dependent sources, just to clear that up. So thank you for that question. That's very useful. Anyway, so beta is defined effectively, so we've got alpha, we know we've got alpha going through here, so therefore we must have 1 minus alpha coming out of here for it to add up to 1. And so we can just say that IC over IB is defined as alpha over 1 minus alpha. And alpha over 1 minus alpha becomes just the definition of beta. It's not clever, it's just definitions. Right, so what about an NPN device? So we've been considering holes up to now. We might not have realised, but I did mention it. If we consider with an NPN device, then we should probably consider electrons, which is, if you like, is negative current, and this is where it starts to get a little bit confusing. But fundamentally it's all the same. Got the wrong way. So if we consider it with electron current, we basically just reverse the arrow. So what's gone on here is if we go from hole current to electron current in terms of definitions, so this is what we had originally, and then we just reversed the direction of the arrow, and now you can see that IC and IB go into the device intuitively and add up to IE coming out, and definitions still hold from that direction. Right, so I wouldn't worry too much about that. Have a think about it afterwards and just try to follow what's going on. But what tends to happen in most lecture courses is that people will just tell you that NPNs and PNPs are very similar, and you just reverse the directions of currents and voltages in the PNP and it's all the same. But sometimes that's not exactly obvious what's going on. So this is an example of a combined NPN and PNP circuit, just to show you a little bit about how that might apply. So what you should notice, I'm not expecting you to understand exactly how the circuit works. It's really just to show that there's some symmetry between NPN and PNP type devices. So here's an NPN device, here's a PNP device, and you can see that there's almost like a mirror line across here, that everything is mirrored top and bottom in terms of the structure. So this is what people mean by reversing the voltage. So this is being driven by positive voltage, and it's sort of intuitive that you've got a high voltage and the current is flowing through here and then out to ground. and in this case we've actually got a negative voltage, and the current is still sort of will be flowing effectively from here to here, but everything is just sort of reversed. So, and in this sort of case, in this case we've got an amplifier that's amplifying we've got a sine wave coming in based around 0, so there's equal up and down coming in. It's being amplified by this circuit here, but in this case we're only seeing the positive half of the cycle, because that's the nature of these transistors. They can't conduct current in the wrong direction, they don't. And in this one it's the opposite, and we're just seeing the negative pulses, and then we can combine them together, additive in the middle, and we can add these two together to give us the combined version going on. I thought NPN transistors had to have the load on the collector side, and that's why you've come here, because we can dispel myths like that. You can have the load wherever you like on a transistor. It just gives different answers. And where the load is, so the load is what we're talking about, is the resistance here. You can take the output from this side, you can take the output from this side, you can connect these things in all kinds of strange ways. So we will go into the detail going forward about where you put your load and where you take your output, and why, what the differences between different sites actually are. But good to see that people are listening. So in summary then, we can consider a transistor as two diodes back to back, sort of. And we understand now, hopefully, that there's some magic going on here which makes it look like a current source, and there's alphas and betas that are associated with the transistor, and we just have to understand the nature of the alpha and the beta in terms of the quality of the transistor. So a big beta implies an alpha close to 1, but beta can be a number that ranges from, say, can be like 500 or something. And that's an alpha, but they're fundamentally linked. If you know what alpha is, then you can get beta from it. It's very straightforward. So and from now on, you'll be pleased to know we'll be considering conventional current only. So that's the opposite direction to electron flow, but that's okay. That's just normal current. And the take-home points, just to finish this off to now, is that a transistor can be thought of as a current-controlled valve, and the base current, or base emitter voltage, can be used to program a collector current, and the collector current is then fixed at that value until you then change the base current a bit more. The fraction of the emitter current flowing in the collector is called the alpha of the transistor, and the other factor, beta, is just a sort of manipulation of alpha, which allows us to easily, it's for convenience, to get the gain of the transistor. And we'll be using alpha and beta in a bit more detail in the next couple of weeks, and then you'll become very, very familiar with what they are, and you'll be wondering what the problem of definitions was in the first place. So at that point I think we stop, and we pick it up again probably tomorrow, and thank you for listening.